let's see. So, hey, hello. So let me pause. You can move it. Okay. So the previous section, 7.2, we learned this trig integrals. Have two general types. So for these two integrals, it depends on the power. Then we use substitution. Okay. If both of them are odd, substitution in both of them are even. Double angle formula. The second one for this tangent and secant. So if, again, some cases, if m even, if m even, we can split two powers from the secant. If n is odd, we can split one of tangent and one from secant. The remaining case is actually case by case study. Remaining case, m odd and n even trig identities. So we have learned a lot of how to integrate these trig functions, cosine, sine, tangent, and secant. Now we want to utilize this, our knowledge on these trig integrals to do more general cases, more general integrals, trig substitution. The main motivation for this is to get rid of the square root. For example, if you have something like this. Okay, so this, to get rid of the square root, we use a substitution. So and the domain for x is -1 to 1. So the domain for theta will be -2 to pi/2. So we have the domains, and this factor becomes In the general case, we get the absolute value. However, on our domain, here should be theta, correction. Oops. The domain should be theta. On our domain, cosine theta is non-negative. So the absolute value is just itself. You can see for this integral, the trig substitution allows us to get rid of the square root. So from a function with the square root of this to a trig function makes this easier. So something we have done in section 7.2. More generally, if we allow a square instead of just the 1, so a is a positive number. In this case, we use substitution x, a sine theta. Okay, Sakina, for this factor, what's the possible domain for x? Yes, okay, because in the square root, so this cannot be negative. So negative a from x, a. Then in this substitution, x equals sine theta, we have the same domain for theta. In the same way, the square root. Okay, because a is positive, cosine theta is non-negative, a cosine theta. Again, we get rid of the square root. Another case. And Sophia, what's the range for x in this case? Yes. There's maybe steps. What's the first step to find the domain for x?
It needs to be 1 minus a squared x squared needs to be greater than or equal to 0.
Yes. So this greater than equal to 0, this less than equal to 1. So x is from negative 1 over a. X will be 1 over a sine theta. You in this substitution, the same domain for theta. One minus a squared. So we substitute x 1 over a sine theta. Square over there, so 1 over the a square, they cancel each other. And this will be cosine theta. So this is the first type. If you have a square root of the form of something square minus x squared or 1 minus a squared x squared, we can use this substitutions. This is the same class. Okay. Second one, a new one, instead of the difference, we have the summation. Okay, if our function has a square root with 1 plus x squared, so this time we use a substitution. Okay, Sakina, what's the domain for this x? Anything, all real numbers. Then for x, Elisa, what's the domain for, oh, sorry, here should be theta, let me correct. And then I ask you, what's the domain for theta? X from negative infinity to infinity. So here, the point for the substitution is that it's 1 to 1. What do you see for theta? Sakina? Must be 1 to 1. 1 to 1, because it's tangent one period from negative pi over 2 to pi over 2. This is enough. We don't have to go further. We just negative pi over 2 to pi over 2. Okay, now how do you simplify this x squared? Okay, think about it. How do you simplify it? Uh, Sophia, what's your answer for this one? How do you simplify this?
That's equal to secant squared x.
Then to square root of secant squared. Normally, we should have absolute value. Could you determine the sign of this secant?
Um,
Negative, positive, or indeterminate? On this domain, the secant is 1 over cosine. What can we say about the cosine?
it's positive.
Okay, so now we see this just the secant. Okay, so this substitution allows us to get rid of the square root. Let's try an example. Okay, we'll start with simpler one. Let's integrate from negative 1 to 1. Okay, so we have the factor square root 1 plus x squared. Following this suggestion, we're going to use the substitution that x is tangent theta. Okay, this will introduce quite a few changes, and we'll go over them one by one. So first, this factor, by our computation, suggests, okay, I keep using x. Okay, so I should use theta. Do you agree over there, Sakina? They all should be theta. Okay, Sophia, do you agree?
Yeah.
All this should be theta. Okay, I keep using x, but that's incorrect. Have use a substitution. Let me make corrections. Okay, so the factor becomes secant x. Okay, Sakina, what's dx? X is tangent theta. How do you find the dx? Okay, d tangent. Okay, step by step, this will be secant theta d tangent theta. So this is Now we need to match the lower limit and upper limit of the integral. Previously, so x changed from -1 to 1. X from -1 to x1. What happened to theta? How did the theta change? So, what would you say? Do you have some idea how to find the lower and upper limit of theta? We have to match the limits. So when x is -1, how do you find the theta? Tangent inverse -1. So here, this is why we need to restrict ourselves to a smaller domain. On this domain, the function is 1-to-1, so it's have an inverse function. Okay, so for some angle whose tangent is 1, what's that angle? Okay, very nice. And Sophia, for some angle, the tangent is -1. What is that angle?
It's
Mm-hmm.
-π/4.
Mm-hmm. Yes. Okay, that's how we find the lower and upper limits of the new integral in the new variable. Use this 1-to-1 correspondence. Previously, from -1-to-1 for x, for theta is the arctangent, and we compute -π/4 to π/4. This is very important. You have to keep the limit changes with the variable. Okay, let's match this. Okay. And we have integrated this one before. Let's find the formula and just copy this. This is Q. Uh-huh. Let me think about this. This domain. Okay. Oh, sorry. That's the antiderivative. We evaluate this at the two endpoints. Okay. It has been a while since we last time used this notation. Can you recall what this means? So this is a function, a long bar with lower and upper limit. What does this mean? Sophia, do you remember this? The notation. So
Well,
F.
you plug in π/4,
Okay, yes.
and you plug in -π/4,
Mm-hmm.
and then
Okay.
you subtract it.
Okay. So at power 4. simplify. Secant power of 4 is the 1 over the square root of 2. 1 over cosine. Tangent is just 1. Logarithm. Okay, I will simplify the square root of 2 plus 1. Subtract 1/2. This is the same thing. Negative 1. Okay, so simplify, we get square root of 2 minus plus. Minus plus is a minus. Okay, so we can combine this. And 1/2. Okay, the competition is a little bit long. It has been a while since we do this definite integral. So we spend some time, finish the integral. Okay, put them in one screen. Okay, this is a very complicated integral because we have no idea what the antiderivative or in-depth integral this is. So we use this trig substitution, x equals tangent theta. In this way, we change the integrand from the square root to a secant function, x tangent theta. In this way, we get rid of the square root. So from a square root integral to a trig integral. And we found this before. Then we change the limits. Previously for x, it's -1 to 1. But we find for theta, it will be negative power 4 to power 4. Then we add them together, put everything together, we find the difference. So from this step forward, it's just algebra calculation. It's not calculus. Okay, let's do another one. This one is 1 over. Okay, I will give a minute to try this, and then we will work on it together. Okay, Sophia, where do we start?
We substitute x for tan theta.
Okay, what's the new denominator in terms of theta?
It's 1 plus tan squared theta, the square root of that, and then that simplifies to secant of theta.
Sakina, what about the limits? How does this change to theta? Yes, so x varies from -1 to 1, and theta varies from negative power 4 to power 4. This is why we have to emphasize in this substitution, there must be 1 to 1. if we so tangent function, the domain we can extend it periodically, but we have to focus on one period. On this period, it's 1 to 1. This will be so 10 secant square over secant just secant x. Secant theta d theta. Okay, let's maybe try to recall. Could you recall indefinite integral for secant? Sophia, do you remember this? If no, we can go over to check to look up our formulas.
Secant
Is it? Mm-hmm.
Is it secant cubed or something?
So this is a tricky one. We tried several attempts, and before we can find the formula for this, the very tricky one is logarithm. Oh, you're right. Okay, so that's the indefinite integral. And we find the value at the two endpoints. Okay, Sakina, how do we find this? The steps. Mm-hmm. So again, by the formula, the difference, lower and upper, it will be the value at the upper, subtract the value at the lower. So it will be the value at the power 4, subtract the negative power 4. Okay, let's evaluate. This will be 1, square root of 2. 1, negative 1, 2. I changed the order to make it more symmetric. Okay, another definite integral using the trig substitution. After substitution, we get a trig integral. And using what we have learned before, we know what the result is. Okay. A slightly more general case, let's just find what substitution we should use. If we have a squared plus x squared, a again is a positive number, what substitution should we use? Sakina. If we compare with what we have done before, if it's, okay, where it's over here. If it's 1 plus x squared, we use tangent x theta to get rid of the square root. Now it's a squared plus x. What should we use? How do we get rid of the square root? Could we use tangent? Then it will be a squared plus tangent squared. No, it doesn't work. Sophia, what would you do?
You make it 1 over a tangent theta.
Okay, so on the right direction, we want some coefficients. We still tangent theta will be there. Want something to make a common factor a square. So we can put this a square out.
Oh,
Live with. Okay, yes, this will be a tangent theta. Again, the domain will be negative pi over 2. a squared plus x squared. So Kina, using this substitution, what's the result? How do you simplify this? I have a squared here, a squared there. So we can pull out this a squared. It will be square root a squared, the remaining 1 plus tangent square. Now we have, because a is positive, a is positive, so it's just a. On this domain, this is the secant square, secant is positive, just the secant. Okay, so if we have a variation, instead of 1, have a square here, then our substitution will be a. Let's try 9 plus x squared. What is our substitution, Sakina? Okay, 10 will be there. Something else? Okay, so here let's compare the formula. A squared plus x squared have 9. If we want to match this, what will be a? Mm-hmm. If I say a squared plus x squared is 9 plus x squared, how do you find this a? 3. Okay, so that is what we're looking for. This will be 3. Okay, another one. We want, if you are given the following in the integral, 1 plus a squared x squared. Okay, Sophia, what substitution should we use? Yeah, we want to get rid of the square root.
We use 1 over a 10 theta.
Again, the domain will be negative 12, 12. Now let's try 1 plus 9x squared. Okay, so again, how do you get rid of this square root? What substitution? Tangent theta, some coefficients. 3 for this case or 3 for this case? What's the difference? So I move the 9 from the first position to the second position. It's 1 over 3, yes. And we can check. We can check if we plug in 1 plus 9 x squared. X squared will be 1/9 tangent square, right? Then 9 cancel with 9, get 1 plus tangent square. And this is secant. Okay, that's the second type. The third type, x squared minus 1. If we have a factor like this, again, we want to get rid of the square root. What we do, again, we use the trig identity. The identity, we know that if this x is secant, then x squared minus 1 equals to secant. Again, I should use theta, not x. Theta secant theta. So this would be tangent square. Could we drop the absolute value like we have done before, or should we be more careful here? Okay. Before we even start, we should ask ourselves, what's the domain of this one? Okay, Sakina, what's the domain of this one? Okay, so this is greater than 1. Oops. And Sophia, do you have other domains for this one? Yes, okay. So Sakina, she found it. Have two choices. Either it's bigger than 1 or it's less than -1. Either of this works, but this will give us two different domains. Okay, if secant theta, for this to be bigger than 1, we use the domain. On this domain, we have a one-to-one correspondence from x, okay, to theta. And still on this domain, tangent theta is positive. So the absolute value will be just tangent. This one, you can check after class. What's the domain for theta? How do you simplify tangent theta? Not difficult, but you have to go through it. Okay, for the moment, we will make the assumption that we are integrated on this domain. So we can use the substitution, we can drop the absolute value. And let's try. Which one should go first? This one, the integral. Simplest one. Okay, let's find this integral. We will use the substitution. X equals secant. And let me integrate from 1 square root of 2. Okay, we use the substitution. X is secant x. Okay, using the analysis we have done before on this domain, this is the domain for theta, the square root becomes tangent. Okay, so this goes to tangent. Okay, that's the easy part. Let me copy. Okay, Sophia, how do you find dx? X is secant. So what's d secant? Something d theta. What's the derivative of secant?
Tan
Tan and secant. Okay.
secant.
Again, we need to match the limits for x with theta. When x is 1, what's the secant? What's the theta? Think about this. Okay. Let's think about it. How to find this theta? For some angle, with the secant is 1. Secant is 1 over cosine. So what's cosine theta? Okay, yes. So that's correct. Let me put a few more steps. It's the same as cosine theta is 1, then theta will be 0. Okay, the upper limit, secant is square root of 2. So, Sophia, how do you find this theta?
Yeah,
What's cosine theta?
1 over square root 2 is 2.
Mm-hmm.
Square root 2 over 2.
Mm-hmm. So what's theta?
It's
Pi over
4.
4. All right. Okay, so we found the new limit. Move it a little bit. Okay, so it will be 0 pi over 4. Okay, this is a key step. If you miss this or you get this incorrect, then it's impossible to get the correct integral. Okay, now we rewrite. This is 0 pi over 4 tangent the square secant theta d theta. And if you go back to our notes, we have this integral. This will be, let me copy the formula. Give some time. Done this before, so I skip the steps. Again, this notation, it will be the value at the top upper limit, subtract the value at the lower limit. At the power 4, to find this is at the power 4, this is square root of 2, 1. Subtract at 0. This will be 0. Okay. It's a kind of log 1. What's this number? 0, 0. So this term all 0, only this term stays. Okay, so this is the integral. Again, we use this trig substitution. Not easy. However, this trig substitution convert this integral with the square root to a trig integral. And we have found it in the previous section. We can move on to find the value. Okay, so this section we extend what we can integrate. Previously, we can only integrate polynomials. That's easy, x to square x cube. We know how to integrate this. Then in the 7 point in the previous section, maybe chapter 5. Okay, maybe a summary here. Chapter 5. F theta fx for very simple function. For very simple functions, if we can find the antiderivative, we can find the integral. Then in this 7.2, trig integral. Okay, we want to convert some of them to polynomials. Then we know how to integrate. In this way, we enlarge what we can do about the integrals. Then in this new section, 7.3, we trig substitution. We convert this trig integrals. So step by step, we allow more and more functions from a very simple ones, sine, cosine, exponential. Then we go to this powers of sine, product of sine and cosine, product of trig, tangent and secant. Then we go to the square root. We allow more and more difficult integrals. Why do we do this? Because in the real world, in the applications, in physics, in mechanics, in engineering, they have much more complicated integrals. You have to be able to do that. So this is the training. Okay, so the next section we learn another very interesting class of integrals, a new method, integration of rational functions. Okay. The method is called partial fraction. Okay, so let's have 5 minutes break and we resume at 55 for this new section. Okay, so we have 5 minutes break. Resume. Okay, so the integration by parts. So first, let's prepare ourselves to try to recall a few integrals. Okay, start with Sakina. 1 over x, what's the integral? Okay, and normally we will, if x is negative, we should use absolute value. And Sophia, 1 over x squared. What's the
X.
Okay, you see. Think about it. Okay, think it again. What's the antiderivative? Something whose derivative will be 1 over x squared. Okay, what's your guess? something, the derivative will be 1 over x squared to the power -2. Something with derivative, the power becomes -2.
X at 1 over x.
Mm-hmm. Okay, so correct direction 1 over x. And if it
times negative
mm-hmm.
1.
Okay. Okay. The integral. So you should be careful. You can see from 1 over x to 1 over x squared, the indefinite integral changes dramatically. So this one is a very special. Now let me change this a little bit. 1 over x plus minus 1 was the integral. Sophia.
L and x minus x.
So this time, so logarithm absolute value x minus 1. We just change this x to x minus 1. We can use the substitution. If we use substitution, u equals x minus 1, then we get logarithm u. Then we substitute back to x, logarithm x minus 1. Okay. A general case, x plus a dx. So okay, now what's the integral of this one? X plus a, again we use absolute value. Okay, next one. 1 over x minus a squared dx. Sophia, what's this integral? 1 over x minus a squared.
It's ln,
Okay, ln.
or is it negative
Uh-huh.
1 over x minus a?
Yes. Again, we can use the substitution. We can introduce a variable u equals x minus a, then apply this method negative 1 over u plus c. Then we switch back to x negative x minus a plus c. Okay, that's how we find the integral. Difference. Integral of 1 plus x squared, if you remember this. Okay, now let's try to go through our toolbox. Whose derivative is 1 plus 1 over 1 plus x squared? Someone's derivative is this. What's that function? Guess one? So someone whose derivative is this. Okay, so it's a highly non-trivial one, and we will encounter it many, many times. It's arctangent. Sophia, does this ring a bell to you?
Yeah.
Okay. Let's try something. How do we find 4 plus x squared dx? Not easy. We know this one. Could we use this as a guide for us to find this integral? the difference between this, we want to make this 1. We have 4. What we do is we will pull out the factor 4. This will be 1 x squared over 4. Okay, let's do this step by step. We want to move towards this direction. Towards this direction first, make this 4 and 1. We have 1 over 4. We pull out a factor 4. So now what's left? 1 plus over 4 dx. Okay, nothing changes. We just pull out the constant 4. Then again, we want to make a square over there. Squared, this will be x over 2 squared. Okay, another step. 1 over 4. Okay, nothing changes, just the algebraic manipulation. Then we use substitution. In this integral, 1 plus something square, we get arctangent of that thing. So if this will be u, over 4, 1 plus u squared. So x equals 2u. What's dx in terms of u, Sakina? If x is 2u, dx, how does this change? Okay, what's the derivative of x with u? So this time just 2 du. So we can replace this by 2 du. Okay, now so we are in the correct setting. So it's 1/2 1 plus u squared du. And we know by this formula, they give us arctangent u. Then we switch back to x. Be 1/2 arctangent u is x over 2. Switch back to x. Okay, so this is the integral 4 plus x squared. So we use a substitution. Okay. Another one. 1 plus, let me see. 1 over 4 plus x squared dx. If we check this formula, could you guess an integral for this one? How the integral changes? So how the integral changes? If it's 4 plus x squared of 1/2 x over 2, what do you have 1/4 plus x squared? Think. So 4 go to 1/4. It will be the 1 over this. So how does this change? So the result should be 1/2 becomes 2 arctangent 2x. Let's see. And after class, you should verify this following the same step. Okay. And more generally, 1 plus a squared will be 1 over a arctangent x over a c. Okay, so some review of this integrals. Now we will go to a general rational function. Okay, so Kina, how do you define a general rational function? How do you represent it? When you say the rational function, what does that mean? Have you seen it before with rational functions? Okay, you know what the rational numbers are, right? Rational numbers will be p over q. The rational function will be the quotient of two polynomials, px, qx, where p and q are polynomials. Okay, a simple definition. We want to separate two cases depending on the degree of the two polynomials. We say it's a proper. Proper polynomial. No, proper rational function. If the degree of the numerator, the degree of a numerator, degree of the denominator. Here is the degree. Okay. We compare the degrees of the numerator and denominator. If this is smaller, then we say this is the proper rational function. Otherwise, we say it's improper. Let's see an example. A simple one. Okay. Sophia, according to this definition, this rational function, is it proper or improper?
It's improper.
Okay, it's improper. Whenever it's improper, we can use this long division of polynomials to convert it to long division of polynomials. Okay, x cubed. There's no square term. No x term to 0 and no constant. We divide x minus 1. So Kina, have you done this before? Long division for polynomials. So let's go over where do we start? What's the first step? X cubed, x minus 1. Okay, nice. X squared. So this will be x cubed minus x squared. The difference, difference 0. So this is 0 minus negative 1 will be positive 1. Sophia, next step.
You do x
X squared minus x again it's 0 minus -1 to be x plus 0. Okay, so now I can see just 1. It's x minus 1. 0 minus -1 is 1. So in this way, we have the quotient and the remainder. We can write this as okay. So if we want to integrate this part is always easy. We just need to integrate, focus on the integration of this one. More generally, if you have a polynomial, maybe it's improper, but we can use the long division to find a quotient and a remainder. Quotient. By long division. Polynomials. So here, this quotient are the remainder. And the degree of R is less than degree of Q. So when we want to integrate this part is always easy. It's a polynomial. So we will focus on the integration of this. So in the following, we will focus on the integration of a proper rational function. Proper rational functions. Okay, so why is this important? Why is this important? Let's recall the unfinished integral we encountered last time. Why is this important? The first attempt we introduced is we use the definition of secant, 1 over cosine x dx. So we make up a factor, so the cosine square x dx. Then we use the substitution, du y minus u square. At that moment, we couldn't continue. We don't know how to integrate this rational function. And we don't have the formula for this. 1 minus u square. How do we integrate this one? Okay, to integrate this, let's look at the denominator. 1 minus u square. So can I factor this denominator? Oh, nice. 1 plus u and 1 minus u. If, okay, a big if, not sure at the moment. If we can break this 1 over minus u square. Complicated, have no idea. If we can break this into 2 parts, something unknown, then we can integrate these two separately. The integral of the addition will be the addition of the integrals. If we can break this into simpler parts, we can integrate them one by one. And this step is the partial fraction to break a complicated rational function to simpler ones. Okay. This step, partial fraction decomposition. I think it's discovered by Leibniz. Okay. Okay, let's make it work. Let's see how it works for this special example. We claim it's the combination of the two. We don't know what it is. So let's use the unknown. A, we don't know. B, so A and B to be determined. Okay, next, we want to figure out what is this A and B. What this A and B is, we use suggestions. How do you find this? Okay. Yes, yes, yes. Nice. So to find this A and B, we get rid of the denominators. So we multiply both sides by this factor. This one will have 1 plus u, so 1 minus u stays. 1 plus u stays, 1 over there. Okay, so we get rid of the denominator. We have, okay, that's a very important step. Okay. So this is true for all u. There are different ways to solve this equation about A and B. The first way is we can rewrite this polynomial. So constant will be A minus AU, B plus BU. So this will be A plus B plus negative A plus BU. Then we compare the two sides. On the left, because there's no u, you should view this as 1 plus 0u. 1 we compare the coefficients, we see that this negative A plus B is 0 and A plus B is 1. We compare the coefficients. Polynomial, not a polynomial. Okay. How do we find A and B from this system of equations? What do you suggest? Okay, if we add them, they cancel each other. 2b equals 1. We add them. B is 1/2. And from the first equation, we know that A equals B, 1/2. Okay, now we have A and B. We can go back to find this formula. We have the A is 1/2. Okay, let's put the front. A is 1/2, 1 plus U. B is negative 1/2. B is also 1/2. 1 minus U. Okay, so this is the partial fraction decomposition. Sophia, any question about this step?
No.
Okay, very good. So with this at hand, we can go back to complete this integral. I'm going to copy this over there, and we will see how we integrate it. Back to the integral. We have the secant. We use the substitution. U is sine x. Yes. 1 minus u squared du. And then we figured out the partial fraction decomposition. The integral of the summation is the summation of the integrals. Okay, so the first one is easy. What's this integral, Sakina? Oh, nice. Again, absolute value. Absolute value, yes. So I have n plus u. Easy, but the second one is tricky. Okay, Sophia, let's think about it. How do we integrate this one? Is it just ln 1 minus u? So here is 1 minus u. To make this what we had before, let's see, over there, over there, we have this x minus 1, x plus a. If we have 1 minus x, we have to pull out a negative sign, negative 1, x minus 1. So there will be a negative sign. Let's go back to there. So to finish this integral, this is the negative u minus 1 du. Now it's in the correct setup. 1/2 minus 1/2 u minus 1 du. Not du. We have done the integral, just see. Okay, then we switch back to our x variable. So this is 1/2 logarithm 1 plus sine x 1/2 logarithm 1 so sine x minus 1. Okay. Because the sine is between -1 and 1. This term will be non-negative. We can drop the absolute value. Agreed? Because the sine is from -1 to 1. What about this one? How to drop the absolute value of this term? Sine x minus 1. Could we just drop it like this? Sophia, what do you see? How do I drop the absolute value of this term? The previous one's easy because sine from -1 to 1, so 1 plus this is non-negative. Could you get a non-negative function from here?
It means that has to be pi over 2.
Okay. So again, so it's the trick. Okay, it's a little bit tricky to this one. If we look at this one, sine x is from -1 to 1. So -1 is always negative. To get absolute value, we have to flip the sign. To get absolute value, have to flip the sign. We end up with 1 minus sine x. Okay, so we use the formula for the logarithm. It's 1/2 logarithm 1 plus sine 1 minus sine x plus c. And we compare it with the formula comparison. In section 7.2, the trig integrals, we obtained a formula for this. At that time, we obtained a formula is logarithm tangent x secant x plus c. Then in this new section 7.4, partial fraction, we obtain a second formula. Okay. The same integral. Two completely different results. How do we check which one is correct? Which one would you pick? Or are they the same? Okay, Sophia, what's your guess? Same? Or one is more correct than the other? Some mistake happen? And you? So they appear, so these two functions appear completely different.
Yeah.
Tangent, secant, 1 plus sine. But after some manipulation using the trig identities,
They're the
you will be
same.
able to prove the two integrals are the same. And then you will verify this in the homework. Think about this, very interesting. Completely different approaches, however, the same result. Okay, so let me stop recording and check if you have any questions. Sophia, questions?
No.
Okay.